Good morning, everybody.
Good morning, students. Well, it's good we're back in the maybe the standard weather, a little bit warmer. Yesterday felt like spring, and today will probably be the same. So I hope that everybody's doing better. Only in Texas can we get this variation in weather, and it was challenging, and we all suffered through power outages and things that we didn't really expect. But I certainly hope that everybody is getting back into somewhat of a routine. I think when my power finally came back on uh, by late Wednesday evening, I kept my fingers crossed that it would stay on and not just for an hour, and those prayers were answered. So I don't think I've been happier to have electricity. And I always try to conserve my electricity, but I was doing a minimum. I was turning off all the lights and only what I needed. So uh, we we often find in life that though it be very challenging, that we take things for granted. And I have to remind myself many times that just remember that when we have challenges, just like with COVID, they make us stronger. And so I look at this as just an opportunity to be thankful for what I have and what we have. So I'm glad everybody's back today, and hopefully if by the time spring break rolls around, we'll actually maybe have some somewhat normal weather, but who knows what that is anymore. Uh, I've tried to spread out the dates, the due dates. I've put up lectures for the material from last week since we didn't have our formal lectures. So all of that material is up, and I've spread the due dates out a little bit more so you have time to get caught up. Fortunately, the material that was left on polynomials was just basic review material from college algebra, and I think the Smart Pen videos, in addition to the lectures that I have the recordings of on Blackboard, will be very helpful to get you back into the routine of that. So again, think about this as a way of keeping you one step ahead. Always having that extra challenge to make you work that much harder. That's called accentuating the positive, and I do that, and of course you do that too. But work extra hard these days, and before too long, we'll be back into a routine where we feel like we've got some kind of peace and sensibility. So what I want to do today is to begin our review of exponential functions and log functions. And like the polynomials, this again is a review and very, very straightforward. But what I want to do is just make some comments about some things to hopefully enlighten you a little bit, or maybe just remind you about what you already know. So I've actually made a sheet as a summary to start off with. So I'll go ahead and share my screen. Right here, what I've tried to do is just give a little summary of some of the mechanical things that we're going to need to work with exponential functions. Now, exponential functions are what we call transcendental functions in the sense that they have certain characteristics that are unlike the algebraic numbers of the polynomials. So when we talk about a transcendental function, we think about a function that is based upon a number that is not necessarily algebraic. And the number that we're going to be focused on eventually is going to be the natural base, which is symbolized by the E, the 2.7182, et cetera, like pi. And what we know about these numbers is that they are not zeros of integer polynomials. And because that's the case, they have different characteristics. And what's interesting is that there are an uncountable infinite number of them. So we can't even list the transcendental numbers. And it appears that, at least for now, we're only really interested in two of them. Of course, pi will just be all in our face when we start the trig section. And the natural base is actually the base of calculus. And so what we tried to do with the exponential and logs is give you a really solid foundation so you can surge ahead like you will with the polynomials when you get to calculus to learn that much extra material. So what I wanted to do is just give a brief summary and then talk about some of the ideas and problems that we want to do. Obviously, our focus is to solve equations. So what we want to do is lay a foundation that will allow us to do that, just like we found zeros of polynomials, which was essentially solving an equation. So what we're going to start with is a positive number. When I say fixed, that means that it's going to be a constant. So we're going to be interested. Well, here's a famous base that we like based upon our number system. The base is 10, 1, 0. And then, of course, the number I've been talking about, the natural base E, is another distinguished base. And of course, if you use your Google calculator, you'll see the E, you'll see the LN, you'll see the 10, and you'll see the LOG. And so all of these are standard representations of those exponential functions in their inverses. So someone else thinks they're pretty important too. So what we do, as I've said before, is we call A the base. And we're going to define the exponential function rather intuitively because we really don't have the mechanics of infinite series yet to do it formally. So what we're going to think of is if we start with a fixed base, we will define the base A exponential as the base raised to a variable power or exponent, which is basically the reverse of the power function. The power function, the base is variable and the actual exponent or power is fixed like x squared. And we know a lot about those. So this in and of itself is very, very different. And we will define it to actually be, to make sense for all real numbers x. So when we think about this and we try to set up some type of idea about this, I've got some summaries down here. You're thinking, well, there's a whole lot of accepting of what an exponential function is. But at least at this point, we can set up some of the basic qualities and build the function at least to a point that there's some stability in its use. So before we move forward, and of course, as you get to calculus, and even in this class, we would be able to do some proofs of these. But for now, we're going to look at these as basically the laws of exponents, basically like we have for the power functions. And you're going to see that they're essentially the same. So if we're going to let x and y be real numbers or exponents, we're going to have these four definitions. And we may add to this list, but for now, this will be good. For a raised to the 0 power, for mathematical reasons, we're going to define that to be 1. And the three dashes means is exactly equivalent to. That's what you use when you're sometimes writing definitions, and you'll see it again. So you're thinking as we have a positive base and the exponent gets closer and closer and closer to 0, in the limit, we find that a to that particular power approaches the number 1. So we think, okay, do we define this first, or do we look at 2 and 3 first? Well, if we define this first and then we look at 2 and 3, we make sure that it makes sense. And so whatever we define first, we have to be sure that whatever follows is consistent with that definition. So thinking about that, just like with power functions, if we have the same base, we say a to the x times a to the y, we will basically add the powers or add the exponents, x plus y, just like we do with power functions. And again, it gets really kind of interesting when these real number exponents get to be strange numbers like, square root of 2 and 1/2 and things. We're pretty okay with 1/2. We know that's equivalent to square root, but again, very interesting things will happen. Now, if we define this, then it makes sense to define the division with the subtraction. That is, if we take a to the x, same base, divided by a to the y, then we should be able to subtract the exponents or the powers to be consistent with this rule. So again, we're thinking, all right, that makes sense. And then if we basically have a to the x divided by a to the x minus x would be 0. Well, this side would be 1. So we think, okay, well, if we had a to the x over a to the x, let me just write this down, which of course is 1 by definition. But then if we use 3, this would be a to the x minus x, which is a to the 0. So at least with what we have in 3, we see that it is consistent to what we have in number 1. So 1 and 3 are jiving, so to speak. So if we start with this, we need to make sure that this rings true with number 1, and we see that it does. So of course, as you invent new mathematics, if it's going to be any good, it's got to work with what's already there. assuming that what's already there is actually good. So, and then the last one that we find ourselves using often is when we actually raise an exponential function to a power. Just like with the power functions, we multiply the powers or the exponents. So think of having y copies of a to the x, where you write a to the x times a to the x times a to the x. And so that would just be thinking, okay, now I've got y copies of that, so the new power will be x times y. So this is just a shortcut, so you don't have to go back to number two and think about it inductively. So this is basically number two, where we just have the same exponential function multiplied by itself. And all this does is just give us a little recipe to extend to. So that's all that is. So sometimes when we write laws, we tend to be a little bit redundant. And that's just because we want to make sure that we've covered everything and at least completely. Some purist mathematicians are so scant in what they give you that it's like, okay, so I have to extrapolate all these other ideas, and so we don't necessarily want to do that here. Now, one thing I wanted to point out was just the basic characteristics of the exponential function. Now, one thing that's very, very important about the exponential function, aside from the fact that we define it for all real numbers, is that the function a to the x is strictly positive, okay? It does not assume the value zero, nor does it assume any values that are less than zero. So that is a very strange condition, but it seems to be at least very intuitive in terms of how we define it. So we take this positive base and we raise it to powers, okay? So it's kind of difficult to think that if you raise a positive number to different powers, that it's ever going to be anything zero or negative, unless you just multiply it by a negative, like doing a x-axis reflection, which is again what we can do with these functions, just like we did with the previous ones. So that is a very, very important property. Okay. So we must remember that when we think of these particular functions here, for instance, when a is greater than one, we get an increasing function, and that intuitively makes sense, but we need some calculus to verify that. So some of these ideas will not come into fruition until we get to calculus. So the idea is that the case where a is positive, the exponential function grows. They say this is called the exponential curve. Now, one thing about these functions that is extremely important, that also requires that we understand the inverse function, again, calculus, is that they are one to one. Now, again, it's not because I drew it to make it look one to one. It's that I know it's one to one. And so I make sure my picture looks that way. But again, we know that's not a proof. That's flimsy as can be. But we will make that assumption from our definition that the base A exponential is one to one and therefore has a what? Inverse function. And so just by cheating, we can just reflect this graph in the line y equal x and draw the inverse function, even though I haven't given you a name for it. We know what it's going to be, but there's the inverse function right there. Now, just to make some other notes here, the only difference between these two cases is that one increases and one decreases, but all the other attributes are the same. That is, we get nice continuous functions, no holes. They're differentiable in the sense, just like polynomials, nice and smooth. A smooth curve is a differentiable curve. It has no corners, no points. Like if you were driving along a differentiable road, you would not have to worry about any road disasters. That is, you would get to your destination as long as you could drive safely. Now, like I said before, this is always a positive output. And what we're noticing here, which is very different from what I lectured on about horizontal asymptotes, is that the x-axis is a horizontal asymptote. So what we're seeing here, as x tends to infinity, the function becomes unbounded. That is, we can write this in. Here's some little extras. The limit, now that we have this notation, x approaches infinity, of a to the x is actually infinity. This function gets as large as you like. And then as x tends to negative infinity, gets infinitesimally small, the actual outputs converge to zero. So we can say the limit as x approaches infinity, excuse me, let me put negative infinity. I need my minus there. So let me make sure that's there. Negative infinity, a to the x equals zero. So these are two, these are two attributes of the basic base A exponential function. That is, when a is greater than one, it gets as large as you like, but as x tends to negative infinity, the outputs tend to zero. That is, they get smaller and smaller, but never equal to zero. Now, the flip of that, you're thinking, well, this is really a transformation going on here if we get clever about this. But the difference here is that when A lives between 0 and 1, the base, again, 1/2, 1/3, 2/3, numbers like that, the function actually reverses in that it becomes decreasing. And that makes sense because if you take a number between 0 and 1 and raise it to a really large positive power, it gets smaller and smaller. So now we can say the limit as x approaches infinity of a to the, in this case, let me just say, I'm not gonna say anything more. I'm just gonna state the case, a to the x. Now where a is between 0 and 1, and let me focus up here, a is bigger than 1. This actually is 0. This flips around. And then the limit as x approaches negative infinity of a to the x, where x is between 0 and 1, we get infinity. So let me just write something here. Here's a special example. Say we have limit as x approaches infinity of 1/2 x. That's going to be 0. Or we can use the laws of exponents and write this as limit. Just write this as 2 to the negative x, writing 2, 1/2 is 2 to the minus 1, and then using the laws of exponents, we could write it equivalently this way. We could say 2 to the negative x is also 0. And these say the same thing. So what I want everyone to be familiar with is the basic characteristics of these functions. The idea is that when we think about the base being between 0 and 1 and the powers getting positively larger, we think convergence to 0. But the idea is that when we run to negative infinity, the powers invert the base, so to speak. And then, of course, they grow, but again, growing as x tends to negative infinity. So just the opposite of this curve. So those are characteristics that, again, are embedded in the calculus of the base A exponential. But when you take calculus, ladies and gentlemen, you're actually going to learn about the natural log function first and then extend that calculus to the inverse function. So you'll do it the opposite of what we're doing here. So this is probably not the most mathematical way to do it, but it tends to be the convention in pre-calculus to start with exponentials. And most students find the transition to be very easy. It's just that I want you to be aware of it when you get to calculus. If you take my calculus course, the first function that we will talk about is the natural logarithm, which will be defined as an indefinite interval. So there's even more calculus for you. So these ideas here, you remember from college algebra, but it's probably good to just jot these down, put them on a note card. Again, everything is the same except when the bases have certain restrictions, one curve increases and one curve decreases. And notice here, I just used the line y equal x to draw the inverse function. So in this case, the inverse function in red looks like this, just cheating using the reflective line y equals x. So we can make a definition and we can assume certain characteristics and just move with them. And so that's what we want to do with the exponentials. So we need to keep all of these ideas up here because we will need to use them to make good decisions as we work through problems. Okay. So this is good. Hopefully this is something that is a little back in the recesses of the mind. Exponentials and logarithmic functions are fascinating, and you will spend a lot of time on them, at least when you get to the end of Calculus 1. Usually by then you're exhausted and you're ready to stop. But one of the nice things about the WebAssign is you'll get your opportunity to move the curves around with the transformations. Of course, that's very simple. So you'll get some examples using the parent curve of the exponential. So that'll be very straightforward. So what I want to do is spend some time on some things that are a little less straightforward. Now, the first thing we want to do is to consider a compound interest formula, which I think is pretty interesting. So in this example, we want to think of a principal P. So this will be a principal amount of money or a principal amount of money. A will be basically the value or amount value of transaction after a certain amount of time. So sometimes we just call that, what's the amount? What's the value? And then what we want to do is to consider an annual rate of interest. So we're going to say R will be annual interest rate. And pursuant to how finance is done, a fixed N will equal number of compoundings. That is, how often would an interest be levied if you're trying to make some money? Number of compoundings per year. And when we think about maybe standard number of compoundings, 12, for 12 months, but that is usually having to do with an annuity, which this will not be, but credit cards, mortgages, things like that, car payments monthly, which is about all we can stand. If we had interest levied more than that, it would get a little bit out of hand. And then, of course, T will be duration of transaction in years. Now, one thing we like to do is we can say periodic interest. This is how it's defined. Periodic interest would just be the annual rate divided by the number of compoundings. And sometimes we just denote that with a lowercase I. Now, the idea is that when you apply interest, you have the principal plus the amount of interest, and then you add those. And then you apply interest again. This becomes exponential. So the idea, if we think, for instance, where we have, let's just look at it this way. Say we start out with in this particular case, I'm just going to say that we're going to just say a compounding, not necessarily and for a year or whatever, but just a compounding. And so, for instance, when we start out, we're going to have amount over here. So when we start out, we've done no compoundings. We have the principal. So we make the deposit of the principal, and that's how much money we have, what we deposited. And then for the first compounding, we'll say, okay, we're going to apply the interest for that period to the principal. So this is very basic. So you apply the interest to the principal, and then you have that interest plus the original amount. And then you're thinking, oh, factoring, because we factor everything to death. So this will be P times 1 plus I. So the idea is that this is an inductive procedure, and it's actually quite simple. And again, something you learned in your college algebra. So, but again, it's something that's neat to think about, because at the end of this class, we'll do induction. Now, for the second period, we'll do the same thing. We've got the interest applied to the amount plus the amount. So we have I, in this case, times P 1 plus I plus the amount that was there from the last period. And then, of course, you can see we can factor this again. We'll get a P times the 1 plus I, and that'll multiply the 1 and the I. But so this gives us P times 1. Well, let me make sure that's a 1. I'll just do the 1 first. Just, I think that's convention. I don't really think, it doesn't matter clearly. 1 plus I squared. So the idea is that this becomes an inductive process. And if we go, so you can see now that if we have 3 compoundings, this will just be P 1 plus I to the third with the same algebra. So the algebra is very easy. So this just keeps going this way in an inductive process. And so if we wrote a formula, we could prove it by induction, thinking about the number of compoundings. So to make a formula out of this process that is useful to us, we just want to say, okay, if we have n compoundings per year, we would say this would imply that n times t would equal the total number of compoundings. So again, if we had maybe 2 times a year or 4 times a year for 4 years, we would take the product of those 2 numbers, and that would give us the total number of compoundings. So basically what we could do is just take the 1 plus I and raise it to that total number of compoundings, and then multiply it by the principal and get the amount. And so that would be an inductive way to come up with the formula, albeit very simple. It then gives us an exponential function. So this implies that, and this is the notation of the book, even though it's probably not the best, it's not horrible either. We could say the amount based upon the number of years would be the principal times 1 plus, now we can write I as R over N raised to the NT. Now, of course, the R and the N and the 1 are all fixed. That's a base right there. And this is what you don't get in college algebra, because it's never taught this way. That's why we go to the next level in pre-cal, just to give you a few new characteristics. Nothing major, but just making you think of it in a different way. So this becomes the base. And so now we're raising the base to NT. And then, of course, we have this P here, which is like a vertical stretching. So this is basically a transformed exponential. So we say transformed exponential. So when we do finance, we're actually, with compound interest, which is what this is, we're actually working with transcendental functions. So when you become a financier, you have to know a lot of calculus. You have to know a lot of probability. Well, if you want to work, for a nice firm, in a STEM career. And of course, if you go to business school at UT, they require that you have 2 semesters of calculus, which the business students don't like. At Texas A&M, they have to have finite mathematics and business calculus, but it's so hard to get into the May School of Business that it doesn't matter anyway. So it's there's certain disciplines that are overrun these days. Engineering, STEM, business, finance, and medicine. Everybody wants into those areas. And so that's why you carve out a place for yourself. Work hard, but just understand that even if you think you're going into business, you won't be doing as much math. Probably not. You will be doing quite a considerable amount of math. So now, if we look at a particular example here, let's just do a simple example, and I can show you how to use the Google calculator. Say we have a principal of $4,000, and we have interest compounded monthly. So this is going to be an N will be fixed at 12. And then it says the duration will be 6 years. And we have the annual rate of interest is 5%. And it says to compute A, and we always have to pay attention to rounding. Here it says round to the nearest cent, round to nearest cent. Sometimes it says round up to the nearest cent. I mean, it just, like I say, you have to be careful of the formatting because it's important. As a financier, rounding, I think we round too much. I mean, in mathematics, the number is the number, okay? Rounding is something we've just been brainwashed to thinking. Everybody thinks their grade should be rounded up. That is a falsehood. When your grade is calculated, that's your grade, okay? This rounding bit has become rampant, like it's the truth. It's not the truth. It's so unfortunate that we've been indoctrinated to rounding that we don't even know what numbers are anymore. However, when you do your WebAssign, it will say, please format your answer this way. So for instance, if you have a client, the client might say, oh, I would prefer that you round up to give me that extra penny or half a cent or whatever. So again, when we make money for our clients and things, we can't give them a half a penny. It used to be a halfpenny was a half penny, but we don't have those. So our clients should benefit from that process. So when we look at computing A, the first thing we want to do is figure out the base. So first, R is 5%. This is 5 over 100. So 5 over 100, of course, the 100 will absorb the 5 and give us 1 over 20. So now this implies that A of 6 years will be 4,000. Now we can, and of course, before I do this, let's just go ahead and figure out the base and then we'll just, place it in. So now notice we get 1 plus R over N. Sometimes I do this in this calculation, but let's just go ahead and do it to the side just to change it up. This will be 1 plus 1/20th, in this case, divided by 12. That's this calculation here. So of course, invert and multiply. So this is 1 plus, when we look at this, 200 plus 40, so that's 240. So if we get a common denominator of 240, we have a really strange looking base. We get 240 plus 1, so 241. Now, of course, this is not, we don't really work so much with the base 241 divided by 240. That's a little bit odd, but it is a base. And so what we're seeing in this particular problem, that's the base. So now we have 241 divided by 240. And now let's see, we've got 12 and we have, so let's just do this calculation. NT is 12 times 6. So that'll give us a what, a 72. So when we look at this, this is the exact amount right here. This is exact right here. This is exact. There's your crazy exponential. So this is exact. Now, in order to do this computation, you need the binomial theorem or the Newton's binomial theorem. And so what you can do at this point is use your Google calculator. Now, I've pulled this up. Let me show you. Google, just enter Google into your search engine and scientific calculator, and it will come up. So let me get that. Let's see where. Oh, let me see if I can find it. Let me do this. Lots of times I have to move it around because let me get rid of that. Yeah, I have too many things open, and then it. Oh, there it is. Cool. So here's the Google calculator. It's just part of the search engine. Okay, I have what, a 471 million results. So now what we can do is just say, okay, we've got 4,000. So we need a calculus approximation times, and then use your parentheses and enter the base 241 divided by 240. This is where we need calculus, and we've got to help out our client. And then we go to the exponent here again, which is the binomial theorem. Exponential functions, when you raise, you're thinking, are we using the exponential function or the binomial theorem? When you have the one plus this plus a number, that can be treated as binomial or exponential. So both of them require calculus. And so now our power is 7.2. Now, as long as it's not some algebra with the power, you don't have to put the power in parentheses. But if there's algebra there, you do. And this will give us 5396. And to the nearest cent, this will give us 539607. So that is the only calculation that we need to do where we have the Google calculator. So again, the focus should be this, and then the estimation at the very end of the problem. I don't understand, again, if you were doing estimations in getting to this point here, then that is patently false. And I do not teach that way. I get a little upset when there seems to be a run to a calculator as if you don't know how to add. So make sure that just like in all the problems you do when you're doing a calculation, that you keep your computations exact. If you're in a science class and you get all crazy with rounding, your science professor is going to say, well, that makes no sense. What have you done? So you don't even want to do that in your other classes. So again, work to the exact answer and then use your Google calculator to approximate, to give a nice calculus approximation. Okay, so there we have it. Now, what I want to do is say just a little bit about the natural base. But before let's see here, there's a difference quotient. Yeah, that's useless. You know, there was one problem where when you do calculus and you figure out the calculus of the exponential, you don't use the difference quotient, you use the inverse function theorem. So there's a problem in WebAssign that you're going to do, but you'll probably do it once and that'll be it. It'll just be a nice algebraic example. Now, so when it comes to dealing with exponential functions, that's a nice application. And what I want to do is introduce the natural base and then parlay that into what we call continuous interest. So when you think about the natural base, you're thinking, well, you're going to define this like geometry. You know, what's pi? It's the ratio of the circumference to the diameter of the circle. That's a fixed constant. Well, E is not this way. Leonhard Euler actually discovered this number, and the E his name, German name, Euler, Euler, that's why we call it E. So this is where the E came from. Leonhard Euler was like Archimedes, Carl Friedrich Gauss, and Sir Isaac Newton and Leibniz, one of the greatest mathematicians who ever walked this planet. Probably the most contemporary person that we're aware of is Srisivana Ramanujan, the Indian mathematician, again in the 20th century. But we have a lot of smart people walking this planet, but these were true gurus of mathematics. And Euler, like Newton, put out so much work that it was impossible to keep up with it. So what we want to do is define a base that Euler discovered. And you can actually define it as the limit of a sequence. But what I'm going to do is I'm just going to define it as a real limit and let x pass to infinity. So we're going to say the limit as x passes to infinity of 1 plus 1 over x. And of course, when we do asymptotes, this is where we start using this nice notation. And I know it's very intuitive. And when you get to calculus, you're going to put all the arithmetic behind this. So you'll actually have a more thorough understanding. But for now, intuitively, it's very nice. We say, what happens to this expression, 1 plus 1 over x raised to the x power, as x gets larger and larger and larger? And you're thinking, well, that's really going to go to 0. So 1 to the infinity, is that 1? Well, no, it's not 1, it's e. And what we're going to find is you can prove this limit using L'Hopital, or you can use the monotone convergence theorem from real analysis, treating this as a sequence. So there are many ways to actually prove the existence of this number. And this number, like pi, is transcendental. And we think of an approximation 2.7182, and this goes on forever. Okay, like pi, 3.1416 dot, dot, dot. So again, this is a transcendental number. The calculus here is daunting. So the idea is that what we do in pre-cal is give you enough foundation so when you get to the calculus, you can work that understanding into the arithmetic and be very comfortable. So when we think about this, we're thinking, okay, well then we can just have a function f of x equals e to the x and just be nice and happy with that. And of course, this e is bigger than 1, so it has the nice curve that we think it would have. I mean, this is, the idea is that the basics of the exponentials are just easy. And so we have the nice exponential function. So we say y equals e to the x. And of course, we can just do the y equal x. There's 0, 1, so we get 1, 0. And we can just go ahead and draw the natural log function. Now, later on, I'll say what this is, but here's the notation we used for this, ln of x. And that makes hardly any sense, but I'll say more about that later. We come up with some crazy notations in mathematics, and I apologize for that, but you get used to it and then you're fine. Now, so why E? Well, the thing about E is that it comes up in finance, it comes up in calculus, and the thing is, this base is the base of calculus, like pi is the number for Euclidean geometry. This base turns out to be the base of calculus, which defines all other exponential functions and defines all inverse functions called the base A logarithms. So what Euler discovered was huge. Okay, so we didn't just pick this number out of the blue because we were bored one day. This number is the base of calculus, and so we spend time on it. Again, there's a reason why you study what you study in pre-cal. Somebody did actually think about this. Now, why, so basically all the rules that we have for the any base work for this one. So nothing new there. But how does this impact the last formula that we actually worked with? So now we can say, what happens? This is a fun calculation. What happens as the number of compoundings proceeds to infinity? So we might think, if we do more compoundings, more than 12, you know, can we make more money? And you're thinking, well, yeah, we should be able to make more money, but there'll be a limit to how much money you can make. And so banks don't normally use this. They just use the standard 12 compoundings or maybe more, but not necessarily the continuous interest. There are uses for it. But what we're seeing is that because this number is actually defined, there is a cap on how much money you can make. And so let's figure out what that is. So for instance, we'll say the limit as n approaches infinity of our compound interest formula. This is just some basic algebra that I want to talk about. That'll be easy. Now, when you get to calculus, the main thing here, when we work with the algebra here, is that the n's vary, but the r, the p, and the t relative to n are constant. They do not vary. So we always have to be aware of what is actually changing in a limiting process. So what we can do, and this will be something you'll learn in calculus, but it's very intuitive, is that we want to move the limiting process inside by what we call continuity. And so we're basically going to get 1 plus r over n to the n, and then use the laws of exponents to put the t on the outside there. So basically here we factor the p because it's just a constant relative to n, and we move the limiting process where the n's actually are varying, and then use the laws of exponents that we had on the first page to move the t out to the exterior. And now we're thinking we need to use this somehow. So how do we get that to work? So what we want to do is think about, well, if we wanted to define an x here, it would need to be the reciprocal of this. So we're going to say, let x equal n over r, the reciprocal. Then equivalently, if we look at this and think about this, notice in this particular case, if n goes to infinity and r is fixed, x will also go to infinity. So this will equivalently say that x passes to infinity. So now if we make that change here, we now see also that n equals x times r if we just solve for n. So this will give us a way to transform this computation right here into the variable x to match this. So now let's write it. So we have p, this is the limit as x approaches infinity, 1. Okay, of course, this is x is n over r, so r over n is just 1 over x. Obviously, you see why I made that. There's a whole lot of common sense in calculus, which, again, when you take calculus, do not leave your common sense at the door. Bring it inside, as we did with the limit, and think about how we can use the algebra. And now notice the n is xr. So we can say x r, but now let the r join the t outside by the laws of exponents. So the n becomes xr, so we have xrt, but again, by the laws of exponents, we can just move the r to join the t. And now what you see is inside here is exactly that. So what I want to show you is that when we do algebra, we're actually doing the mechanics of calculus. And that's why you might think, well, why do we factor everything? Why do you work with arithmetic all the time? Because that's what you have to do in calculus. And if you can't factor and can't do the arithmetic with confidence, it's okay to make a careless mistake. We're all human. That's going to happen. But I want you to now see that we have the definition of the base E right here. And so now we can use the definition. So this is P, this part's just E, E to the RT. So all of this right here, this equals E based upon that. So now we've got this nice continuous interest formula. A lot of students call this the PERT formula, P-E-R-T. Well, so when the interest is continuous, so we call this continuous interest. And so what's nice about this formula, it's actually easier to use. It's actually easier to use than the compound interest formula because there's no n. The n passed to infinity, and then we get the amount with continuous interest is P, the principal, times the exponential function E raised to the RT. Again, T being the variable for the duration, just like we had before. So if you want to use the notation of Dr. Stewart, again, it's not the best, but it's, again, like I said, it's not horrible. This is A of T right here. So we can think of this as the continuous interest formula. So again, when we think about problems like this, and you can, again, do it just like we did before, but now you can see that when you think about interest problems, and if those of you that go into maybe business or finance as your STEM career, you're going to think, okay, well, I'm going to be stuck with the natural base because it's actually part of the continuous interest formula. So we see here that the connection is based upon this calculation here, which again is just a lot of intuitive algebra. So again, think about this as a way to introduce yourself to the base E, which is the standard base, which is the calculus base, which is what we study to provide the calculus for all of the other exponential functions. We start with the base natural logarithm, base E logarithm, and then move that into the base E exponential. So it's all set up for a reason. Now, I wanted to say something about a couple of examples here where we just basically have a nice formula where we can use some of the characteristics that we know about the exponentials. And this is a good one. This is a nice example from your WebAssign. So let's try this. Move this over just a little bit. There we go. So here's an example. This is a formula, kind of like we had the fish population. This is the bird population. Remember that funny problem, back at the very beginning with the fish population and when all the fish had died, just an interesting problem that was quadratic. Very interesting problem. Now, what we want to do is that we're going to have a bird population, which is going to be based on T. And in this case, we're going to have, in this particular case, T is the time, and we're just going to say, in this case, measured. I don't really know what the actual measurement is. I think it's measured in years, T in years. And the actual formula looks like this. So it's going to be 6,600. And then we have, let's see, how's it written? I'll write it the way it's actually written, and then we're going to change it up. 0.5 plus 21.5 e to the negative 0.043. All these are exact t. So this formula has an exponential term in it. That is, we have a 6,600, we have a 0.5, a 21.5, and then we have the power of the exponential negative 0.043t. So as t gets larger, this is going to decrease, as we talked about on the first page, converge to zero, so to speak. Now, to move this forward, let's first do some little computations. We're going to say 0.5 is 1/2. 21 and a half will just be what, 42. So that's going to be, in this case, 43 over 2. So 42 plus 1. And then, of course, 0.043, we can just write as 43 over 1,000 to make the numbers a little bit more user-friendly. So now we've got 6,600. So maybe you'll be in a differential equations class or physics class or calculus class where you have a function like this. So we have 1/2 plus 43 over 2 e to the negative 43t over 1,000. And again, t is greater than or equal to 0. Now what's interesting about this particular function is that we can intuit some ideas about it. The very first one says this: what is the initial population? Well, this just means when we start measuring, when t is equal to 0, what's the population? So we want n of 0. So let's go to our function. So that's going to be 6,600. Then we have 1/2 plus 43 over 2. And now, of course, if t is 0, we just get e to the 0. So 0 times 43 over 100 or 1,000 with a negative is just 0. 0 times any number is 0. And so now you're thinking, by definition, e to the 0 is 1. So we get 6,600. So we have 1/2 plus 43 over 2. So this gives us 6,600. We can add the 2. This is 44 over 2. Well, 44 over 2 is 22, so we're happy with that. And so now if you look at this, 22 divides 66, the author was nice to us to give us a 3. So this just leaves us with 3 and 2 zeros. So the initial population of birds is 300. Okay, so again, just like with the fish population, we can estimate, you know, for instance, use this as a predictor, just like when we do exponential growth and decay and Newton law of cooling next week, using some of the applications of these exponential functions. And now when you look at this, you're thinking, okay, well, what is this sketch of this curve going to look like? Is it going to look exponential or is it going to be modified? Well, obviously it's going to be a little bit modified because we have a fraction here. But notice, first what we can do, since this is a decreasing function, we know it's going to decrease to 0, that is converge to 0. So we can say what happens as time becomes infinitely large. Well, we can look at our particular function here and just say, okay, well, this is actually fairly interesting here. Notice when we look at this and we think about what's going on, we say, okay, this particular function here will converge to 0. So we're going to say the limit as t approaches infinity, 6,600, 1/2, which will not be altered at all by the t. They have no t in them, plus 43 over 2 e to the negative 43t over 1,000. Well, in the limit, The 6,600 is unaffected. The 1/2 is unaffected. The 43/2 is unaffected, but this term here converges to 0 because it's a decreasing function. That is, the limit as t approaches infinity. This is like I wrote on the very first page. This gets smaller and smaller, and then the limit becomes 0 because this is a decreasing function as t converges to infinity. And so now we just get 43/2 times 0. So this is 6,600, 1/2 plus 0. So 0 times 43/2 is 0. And so this just reciprocates. So this is 6,600 times 2. So that gives us a 0, a 0, a 12, and a 1. So we get 13,200 birds. So what this function says, given what we know about exponential functions, our intuitive grasp, and it's actually a very algebraic grasp, but we know we haven't had the calculus, but we still have enough understanding of these functions to be able to work with these formulas here. So we're seeing that there's a cap on the bird population. And this may, some of you future biologists and ecologists will have done your research, and you come up with this model, and your model says, well, the largest this population can be with these environmental factors is 13,200. And you're thinking, wow, okay. So if you wanted to increase the population as a biologist or ecologist, you might have to make some changes in order to support that. Maybe there needs to be a larger food source, whatever. So here we're seeing this is basically a horizontal asymptote. So we did horizontal asymptotes in the last section, and we're thinking, wow, there's this horizontal cap. So what's going to happen? We're seeing, and this is what we need to look at. As t gets larger, this gets closer and closer to 0. So basically we start out, and the function's going to get bigger, 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 because we're dividing by a smaller number each time t gets bigger. So that's going to make the fraction bigger. So it's going to increase and increase and increase and then level off to this number. So note, n of t increases and approaches the value 13,200 asymptotically. So you're thinking, wow, we're doing calculus without having to do calculus, just using our intuition. And that's what's so nice about pre-calculus. You can take these ideas to your biology class and impress your professor. So now let's come up with a real simple scale here. Let's say we've got what, 5,000, 10,000, 15,000. So we just want a reasonable graph, 5,000. And we'll cheat a little bit. So here we'll just say, so like, 300 about right here, it's kind of low. And then the 13,200 about right here. So this will be like a cap. So we can do a little dotted line here. This will be the cap, so to speak, the asymptote. And so what we're going to do is grow, starting at 300, grow. The calculus will give us the actual point of inflection, and then increase right up to this number and hover there. So when we think about this, we're thinking, okay, what's calculus going to do? Well, it's going to give us the shape of this. We know it's going to be nice and smooth because of the differentiability of this function here. But for right now, just using our basic understanding of these functions, we know the graph is going to have a similar look to what I've just drawn without having to be perfect. The idea, if you're doing a lab or you're doing an engineering problem or you're doing a math problem and you just kind of need a reasonable picture of what's going on, you can use a lot of the structure that we've already developed. That is, you take all of this structure to calculus and you bring it into the realm and you use it, and then you spice it up with the arithmetic of the calculus. That is, you'll be able to determine where the shape of this changes from upward concavity to downward concavity using the second derivative. So there'll be a lot of nice things you can do in calculus that we unfortunately can't do now. All right, so that's fun. Now, let's look at the inverse function. I've included a interesting example of the hyperbolic sine in your WebAssign, and you get to show that it's an odd function. It's real simple example. But the idea is that as future STEM professionals, you will contact the hyperbolic functions, and they actually have characteristics that remind you of the standard trig function. So they're really interesting functions. And they're all defined, excuse me, in terms of natural exponentials. So you'll know exactly what you're working with. Now, for the next part, as I stated, we have a one-to-one function. And so when we think about the next couple of sections, which is the base A logarithm, we know that the inverse function exists for the base A exponential. And so we can now define it very simply with the characteristics we know about the base A exponential. So here's our definition. So again, fix A greater than 0. That's the base. So what does it mean? What does it mean when I say fix? That means it's a constant. A lot of times in calculus, you'll say fix this number. It's not a fancy way of saying anything but what I've said. You know, you're testing something. Maybe you're fixing one number and you're letting another number vary. That's what you often do at calculus. Kind of like when we were doing the interest problems. The principal was fixed, the annual rate of interest was fixed, the number of compoundings per year fixed. What varied? The duration. So once you figure out the base for those circumstances, for that particular transaction, then you can let the t vary. And so you can say, well, with my savings account, maybe let me check to see if I let this run for 10 years as opposed to 5, is there enough additional funds that it would be worth, you know, waiting that? Or should I just ask a relative who's got lots of money? So the thing is that as you get older and you develop into your STEM career, you'll make investments and you'll think, well, you know, when I get real old, you know, I want to be a philanthropist and I want to support a lot of good causes. So I'm going to have to invest my money so I can do that. So again, that'll be something you'll think about. So when we think about the fixing numbers, that's a standard construct in mathematics. You're going to find it that it's the case in computer science. You'll find that it's the case in science, physics, chemistry, whatever. So be aware of that. So we define the base A logarithm. Now, Napier was a mathematician who defined the logarithm, and very difficult name to write and spell, logarithm. Logarithm. It's like rhythm, logarithm. We define the base A logarithm, and this is what it looks like. We're going to say y equals log subscript A. That means the base of x. And we're going to use the base A exponential. If and only if, in this particular case, x, oh, and also here we have I'll say more about this. X is equal to, in this case, a to the y. And I'll say more about this. Now, first, note where the x's live. Well, I'll say more about this, but let's just note we have domain of the base A exponential is all real numbers, which will now be the range of the base A logarithm. I mean, we just cheat and use what we already know. We've been doing this since inverses. So there's nothing new. I mean, we learn a new function, but we don't have to learn all the other stuff. It's the same. Functions are functions. And then the range of a to the x, what's the range of the standard base A exponential? Well, it's the positive real numbers. So now this is going to be the domain of the base A logarithm. So that's what I was saying. I didn't include this. So now if I say base A logarithm of x, I know x must be a positive number. Whatever the argument is, the argument must be a positive number. So when you're computing the domain of a log function, you have to analyze the argument, the input, maybe as an inequality, to figure out which inputs make sense. That is, which values of x actually provide a positive input, okay? So the logarithm function feels more restrictive because of its domain. So again, note, the domain of the standard base A exponential is all real. So that means the range of the logarithm is all reals. But however, the range of the base A exponential is positive reals, which gives us the domain of the base A logarithm. So just like we had before in the case, let's just do the case A greater than 1. We'll spend most of our time with this one. We remember what the base A exponential looks like. And then, of course, the logarithm is just a reflection in the line y equal x right here. So very simple. So we would say y equals base A logarithm of x. Now, when it comes to looking at this box up here, that's probably the most important thing I've written down all day. And I say that because it defines the base A logarithm. Notice, when we look at this structure here, basically what this is saying is, give me the actual power of A that equals X, because that's what this says. The logarithm is an actual power. It's a unique power of the base that equals X. So A raised to the Y is X. What's a logarithm? A logarithm is a power of the base. A logarithm is a power of the base. So when someone says, what's the logarithm? Oh, that's a power of the base. So we think about this and say, well, maybe in certain simple cases, it would be very easy to write the actual power because, you know, we can just work backwards from the exponential. So here we would say this would be the log form or logarithmic form, and this would be the exponential form. So moving between the two, at least symbolically here, is a way to isolate the argument. Like here, we've got the x as the argument of the log, and here it's isolated. So this is a way to actually solve equations that are fairly simple. So let's just look at this. For instance, let's take a couple of examples here. Say we have, we'll keep it easy. We'll just take a base 2. We'll say, what's the base 2 logarithm of 1/8? And we're thinking, well, as long as we can rig this input to be an actual base raised to a power, we can figure out the power of the base. So in this case, we'll say, all right, well, this is base 2 logarithm. Now 8, we can just write as 1 over 2 to the third. So that's the base 2 logarithm, or 1 over 2 to the third is just 2 to the negative 3. So the power of 2 that equals 1/8 is what? Negative 3. So this is negative 3. So, so if it's the case that the input is already an actual power of the base, that is the base raised to a power, then we can easily extract the negative 3 here. So we're thinking the input is actually exponential. If the input is exponential with this base, then the logarithm power is easy. The power of the base is just trivial. You simply write this in the form that showcases the actual exponential, and 2 to the negative 3 is exponential. So the actual power of the base is negative 3. So the idea here is that all we're doing is working backwards. This is the reverse path. When you think about an exponential, you input an x, you input the power, and that takes you to the range. And so when you take the reverse path, you got to figure out the power that you actually input down here. So the reverse path is figuring out that power that you input. So that's why we can say a logarithm is a power of the base. So if we can have an exponential input, figuring out the power is simple. Now, of course, this is a nice continuous function. So we're thinking, how do we figure out, what about the ones that aren't neat like this? Well, we can just write them down exactly. And then, of course, we can use our Google calculator to get a nice calculus approximation when necessary. And of course, with the way exponentials and logs are set up, we can always guesstimate about the particular range of where that particular power will lie. Because again, we can look at lower bounds and upper bounds and work that way. So here's another example. Say we have, here's something simple. Let's do this. Let's do a base 3, and we'll do, say, the square root of 3. Now, when you look at this, you're thinking, okay, well, that's already exponential. I'll just write the square root as a 1/2 power. So we'll just say 3 raised to the 1/2. This is an exponential input. The base is 3, the power is 1/2. So power of the base, 1/2. So you can see that the computation of a logarithm in many cases is very, very simple. So we think about this and say, why, what's going on here? We're thinking, okay, well, the power of 3 that equals the square root of 3 is 1/2. What's the power of the base? 1/2. So now what I want to do is say, okay, if this is true, what does this also help us do? Well, we can think of these as inverses, inverse equations. So now we can think, okay, if I compose a function with its inverse, I can have a way of isolating. That is, as I move from here to here, I can isolate the X. If I move from here to here, I can isolate the Y. So this mechanism allows me and allows us to be able to isolate particular variables that may help us move a problem forward. So first we can say, okay, what if we take the base A logarithm of A to the X? Well, these are two functions that are inverses. If I compose the function with its inverse, this is the identity. So the input is X, so the output is X. And of course, the base A exponential is defined for all real numbers. So this is all reals. So that would be an inverse equation. applying logarithms undoes the exponential function. That is, the input is now the output. Likewise, what if I take the base A logarithm of x and then raise that output to the power of an exponential? Well, these are composing functions with inverses. These two functions are inverses of each other. So upon composition, the input is the output, same thing. And so now, of course, we have the restriction where x must be positive. So when we think about problems and we think about looking at particular examples, for instance, we could say, for instance, the base 5 logarithm of x minus 2 equals 2. You could say, okay, if that were true, again, we would know in this case that x must be bigger than 2 for this to even make sense, because the input would have to be positive. But if I wanted to solve for x, I could say, okay, well, here's the logarithm side. I can transpose it to the exponential side. What's a logarithm? It's a power of the base. So the power of 5 that equals x minus 2 is 2. So equivalently, we just say x minus 2 equals 5 raised to the second power, which is 25. And so, of course, you can do this in your head, add 2 to both sides. 25 plus 2 equals 27. So we can see just by defining the base A logarithm in terms of the base A exponential, we can solve very simple equations. And anytime you solve a more complicated logarithmic or exponential equation, you always end up going back to this if logarithms are involved. So when we use this mechanism, we must have one logarithm. It doesn't work with multiple logarithms. We have to combine them. We have to be able to use identities to make the problem make sense. So this mechanism here, which I've used to solve this simple equation, is tantamount to understanding a logarithm. If you understand this phrase right here, then you understand that. And if you don't, then logarithms will just be a figment of your imagination. So be sure that this mechanism makes sense. And now we can see, obviously, this is a correct solution. And so we can put that in our solution set and we're done. So simple problems, simple equations can be solved by just using the definition of the logarithm. So even though we have not defined the logarithm in a formal calculus way, we have certainly defined the logarithm in a very efficient calculating way. And you're thinking, when you get to calculus, is all of this going to get thrown out? No, it will be equivalent. The only thing is that you think of defining trig functions in terms of the unit circle, then you get to calculus and it's like, well, what if we had started with infinite series definitions? Then I would say you wouldn't be able to do all the nice geometric problems. So we define functions in a way that helps us solve problems. And then as we learn more math, we learn different ways to define them, but we certainly don't throw away anything we've already done. We just amplify it. So one interesting thing about mathematics is that you might keep thinking to yourself, well, I'm still studying the same thing I studied in Algebra 1, which are functions. Okay, fine. Well, functional analysis will keep you busy the rest of your life. So we just look at learning more math just to take us to the next level so we know more about what we learned last year. So we just keep edging up. Now, let's do a domain computation. I just made up this problem and I thought this would be an interesting example to kind of hit home about what we've already done. So here's an example where we compute the domain and then we're going to try to compute the range. So we have f of x is equal to the base 3 logarithm. This is really simple. It's a nice inequality that's easy to solve. So when you look at this example, we say f of x is the base 3 logarithm of x divided by x plus 1. And what I'm asking you to do is compute the domain. Now, when I say compute the domain, basically what I'm asking is what values of x would actually give me a real output. So basically what that says is that if I'm going to compute the domain, or if we're going to compute the domain, we must know that the input or the argument is positive. So by definition, we say the domain of f will be all real numbers x such that x divided by x plus 1 is positive. And you're thinking, well, Professor Ron, that's easy. We know how to do this. This is not hard. We know how to do this. This is just a matter of saying, okay, you taught us BVs, you taught us how to solve these, and so that's what we need to do. So now, like, you're thinking, why didn't you put this on the test? This is so easy. Okay, so here we have BVs. So we've got what? 0 and -1. Where's this expression 0? Where is it undefined? So we've got -1. And of course, these zeros have multiplicity 1. So of course, we're going to be lazy again. So we have x over x plus 1. So if you just want to test a simple point, let's just do -10. So if we replace x with -10, that's a negative. And of course, -10, that's a negative. So overall positive. So you're thinking, okay, well, these both have multiplicity 1. So we can kind of, we don't cross because that's an asymptote, a black hole. But then we move into the negative realm. And then, of course, cross here back into the positive realm. So now we say positive, negative, positive. When you use the multiplicities and the behavior in the neighborhood of a 0, it does cut down on the number of points that you have to check. And it is quick, but you have to make sure you get this one right or the whole thing's wrong. So again, if that's not comfortable for you, you can check the points, but it is certainly an efficient way to look at it. So now you can say, okay, well, where are my positive outputs here? That is, if I'm going to replace the argument of this logarithm with x over x plus 1, I'll need my x's to live here and to live here, but I have to avoid the numbers between -1 and 0 included. So this implies that the domain of f will be what? -infinity to -1 union 0 to infinity. So you're thinking, how interesting. This is a really, really nifty problem. And there's a whole lot you can actually do with this problem that might astound you. But what I want to do is to say, okay, if we know what a logarithm is, could we possibly figure out what the range is? Would it be the case that all real numbers would be hit in this case? So what I thought is that when we did this back with the inverses and the functions, we did a similar calculation. That is, we looked at this and said, okay, if you pick some real number, and I called it beta, can any real number be in the range? And would this particular definition exclude something? So let's do it. So what is the range? Now we only do this when I set it up so we can do it. I mean, I'm not going to give you a problem that you can't solve. That's ridiculous. I will always set you up for success using the constructs that I make available to you. So we'll just say, let beta be a real number. So if we took any real number, would there be an input to hit that real number in the range? Now let's test it. So now we have beta equals the base 3 logarithm of x over x plus 1. This is where we get to use the definition of logarithm. That's why I did the last problem with the equation. So we say beta equals the base 3 logarithm of x over x plus 1. What's a logarithm? A logarithm is a power of the base. So the power of 3 that equals x divided by x plus 1 is beta. So 3 to the beta equals x over x plus 1. And I set this up so you can now solve for x, right? So this is solvable. So now we can cross multiply. So again, what's a logarithm? It's the power of the base. So the power of 3 that equals x over x plus 1 is beta. So 3 to the beta equals the argument. That's the definition of logarithm. And that really you should know from college algebra. And if you don't, you know it now. So now let's cross multiply. So we have 3 to the beta x plus 1 equals x. So let's solve for x. Let's go ahead and multiply it out. So we have x times 3 to the beta plus 3 to the beta. 3 to the beta times 1 equals x. Get all the x's on one side. So if you like, we can just run the x's over here. So we get x, and we get 1 minus 3 to the beta. So when we take this over, we factor the x, so we have x times 1 for that, and then x times negative 3 to the beta because we took this over. And then, of course, what's left over here is 3 to the beta. And now we can solve for x if we divide by 1 minus 3 to the beta. So we get 3 to the beta. Maybe not the best choice of letter. 1 minus 3 to the beta. So that's what we have. This is what defines the x's we can use. So now you can look at this and say, okay, well, 3 to the beta better not be equal to 1 because that's undefined. So that would be the restriction. So we'll say if and only if 1 does not equal 3 to the beta. Well, in this case, we say, okay, well, look at this. Beta is a power of the base. So what's beta? Beta is a logarithm. Beta is a logarithm. So this if and only if beta does not equal the base 3 logarithm of 1, right? What's beta? It's a power of the base, so it's a logarithm. It's the base 3 logarithm of 1. What's the base 3 logarithm of 1? 0. Because that's always true. That's always true. That's just using the definition. The base 10 log of 1 is 0. So now we see that the range includes all real numbers except 0. So this was only using the definition of the logarithm. This problem only uses the definition of the logarithm. That's it. So what's a logarithm? It's a power of the base. So we say now the range of f of x is all real numbers except 0. So what I wanted to show you here is that all we have to do is make some really useful definitions, and then we're good to go. Now that we have these distinguished bases, notice we would say for e to the x, we can write the inverse as log base e of x, but that's kind of untoward. What we normally use is ln x, and you're thinking that's about as backwards as can be. Why isn't it NL for natural log? Well, again, that's convention. So we use, when we do e to the x, we use ln of x for the log function as of course, there's nothing wrong with this, but this is the standard convention. And then of course, if we use the standard base, again, when we think of base 10, we often think of we call it the common base. So we say common base. And we call this the natural base, natural base. Now, we could say, all right, we'll just say log base 10 of x, but now the shorthand is to just erase the 10. So when you see log, the assumption is base 10. If you see log on the Google calculator, the assumption is base 10. And later, soon, I'll show you how to change the base. And so it won't matter. When you see ln of x, the assumption is base e. All other bases will be written just like I've done here. Base 3 has no special notation. We just say log sub 3. Okay? So the idea here is that these bases are so distinguished that we give them their inverses special names. That is, these exponentials are standard, but we give special symbols to the inverse functions. Okay? Now, what's really bad is sometimes this is used for the natural base. It really just depends on the book you're using. But I can pretty much tell you that as you pick up most books, the ln will be the natural base and the log will be base 10. That's pretty much the case. So, but you should always check if you're reading a journal article, or you're looking at a journal article on the internet, or you're reading a book or whatever, just make sure that the definitions are what you think. It's always good to check that. So this is a nice problem that just basically showcases the characteristics of the log function, and then it tells you what, how do you use the definition of logarithm? Well, a logarithm is a power of the base. So you can go forward and you can go backwards. See, notice here, we went from the log to the exponential. Here went exponential to the log. A power of the base is a logarithm. So B is the base 3 logarithm of 1. So going forwards and backwards or whatever is what you need to be able to do using the mechanism that defines the base A logarithm. That's all we're doing. And you just, what I tell students sometimes is just when you get to a test, say, oh, okay, y equals base A logarithm of x if and only if x equals a to the y. If you write this down, then you will never go wrong. You can always match this up to what you do here, but you have to think about it. Remember, a base A logarithm is a power of the base. The power of A that equals X is Y. So A to the Y equals X. So that's kind of like the touchstone when it comes to doing logarithms. If you help a friend with logarithms, okay, you make sure you make the definition correct. You're going to do more harm than good, okay? If you tutor mathematics, have integrity. Make sure that you know what you're doing. Otherwise, say, you might need to ask someone else about this. I think I have it, but I don't have it precisely down. If you start with this, then you will help your friend to have a better understanding. Now, I've got an example here. Let's see here. Yeah, I thought this was an interesting problem. And it's actually a problem that has to do with what we're going to do with the radioactive growth and decay. And so here's an example. And this is I like what Dr. Stewart does. He just kind of says, all right, here's an example, but later on you're going to be able to come up with this on your own. So we have the age of an artifact in years. Okay, what we have is D sub 0 will be the original, this is radioactive decay, original C14 content. So what we find is that certain radioactive elements have very long half-lives. That is, they decay very slowly. And so if you can figure out the percentage of that particular radioactive isotope that's available, then you can work backwards to estimate the age. That's what of the artifact. That's what they call carbon dating. And it's very good. I mean, you're not going to pinpoint the day, but you're going to get a really, really reliable estimate. And that's what archaeologists and anthropologists do. And they are truly scientists. And if they're not mathematicians, they've got to have friends who can do the math. And then D will be the actual C14 remaining. So we'll say C14 remaining or present. So when you do your investigation, you find an artifact and you see, basically you have it tested as to how much content there is. And that's how you work backwards. And here's what you find out. You find the following. That is, investigation gives the following. You have D is 66% of the original amount of C14. That is 66% of D sub 0. And here's your formula. A, or the age, is negative 8,267 times the natural log of D divided by D0. So basically, we're thinking of this function that is based upon D. D is what varies. So as you go from artifact to artifact, you're testing or investigating the C14 remaining that's present. So we'll just say present. And then you can use your model to predict the age. This is what we call the predictor. And so now what we can do is the following. So what does this imply? We'll say 66% is just 66 over 100. And of course, we don't have a lot of flexibility here, but we can divide by 2. So we get 33 over 50. So now we can say, all right, so when we want to compute this, we can say at this particular point, so we'll say, let's write to the side, D equals 33 over 50 times D naught. So that's what our computation gives us. This is like what we were doing when we talked about the interest. It's like, what's the base? Remember, we got 241 divided by 240. See, mathematics is all about recognizing patterns, okay? It's not about anything else. And everything is logically connected. So we see an equation, and the first thing we say, what is the pattern? Because if we can't figure out a pattern, we're not going to know how to solve it. So it means like, oh, we got to clean this up and make it more user-friendly so I can use the definition of logarithm. Or we have to rewrite this, so I put it into this form so I can use Professor Ron's AC lemma or the quadratic formula. So again, mathematics is all about recognizing patterns, and that's really what we do. And some of you that love to do patterns would be great computer scientists. So that might be something you consider as a STEM career. So now we have negative 8,267 natural log. So we replace D with 33 over 50 times D naught divided by D naught, or D sub 0. Of course, the D sub 0s absorb, and we have negative 8,267 times the natural log of 33 over 50. Now, in this problem, here's what WebAssign says. It says round. So this is exact right here. This is an exact calculation. And so when we look at this, ladies and gentlemen, we think, okay, we can use our Google calculator that will give us a nice calculus approximation of the natural log here. So this is not a nice input. This is not exponential in base E in an obvious way, okay? So we have to rely upon the calculus that we don't know yet, which our Google calculator will make available to us. So again, we're thinking if we look at this number is less than 1, okay? And so E is 2.718. So when we think of the power of E here, it will have to be a power less than 1 or less than 0, because again, if we start raising E to positive powers, it's going to get bigger. So we're going to have to think of something that's negative to bring the actual value down. So this is using our intuition here. So WebAssign says round to the nearest whole number. So let's go to our Google, and I'll say more about this, what I was saying. Let's go to our Google calculator. Oh, here's the last calculation. Hit all clear. This is so nice and free. So now we have, go ahead and do the negative 8,267. This is where Google is very good to us, times. And then we'll go over to our palette here, Tableau, natural log. And then here we will write or type 33, and you can use your numeric keypad if you have one. I'm just using the mouse, divided by 50. And then of course, close like you do in WebAssign. And this will give us 3,435.06. And this says to the nearest whole number. So this gives us 3,435. So when you look at these types of problems, and of course this will be in years. So again, this is not going to pinpoint the actual day and time, but it gives you a good ballpark estimate of the actual actual age of the artifact. And so again, this is something you've heard all of your life, but think about this. Think about this particular setup here. Notice when we think about the logarithm function, let's just go back to how we define it right here. We know that the natural log of 1 equals 0. Okay? This number is less than 1. So I'm just doing what I was saying before. This is 0, 33 over 50. Okay? So this is what I was talking about before. So we know this is 0 and this is an increasing function. So I'll just draw this picture here for intuition. So now we have what? Again, this is not a proof at all. I don't even know why I do this, but I think it helps. So now we're thinking here, we go down to here. So there's that negative number that we were looking for right there. This is the natural log of 33 over 50. This is a number that's less than 0. And so it absorbs the negative here, and we get 3,435 years. So what we're seeing here is that sometimes the calculations with the natural logs or base A logarithms and base A exponentials may not be as intuitive as we think. We have to keep in mind how we have defined them and how the structure depends on the inputs and the actual bases. So when you're looking at an example, and the first thing you look here and say, oh, okay, this is going to give me an age. And just by looking at this formula, you would have to know that this output here would necessarily be negative to absorb that negative. So when you look at this formula, you're thinking, that makes no sense. Age is not less than 0, but see, that's where the mathematics kicks in. So when I was describing this, I said, oh, it's obvious. Well, maybe it's not obvious. We're reviewing this. So the key here is to think about how we've defined these functions and work from that. So as you get back into this, you're going to think, wow, this is not so bad. But hopefully what we've talked about today is giving you a little bit more insight as to what a logarithm is and how you deal with it. So what are we going to do after this? Well, after this, what we're going to do is we're going to go through the logarithm identities. We're going to find these neat identities that characterize the logarithms, like the exponential rules characterize the base A exponentials. We're thinking there's got to be a counterpart to those with the logarithms, and there is. It's called the logarithm identities. So we, whatever we have here for this function, we have the same for its inverse, adjusted for the inverse function. So we're going to talk about that and then show how we can use those new identities with the definition of a logarithm to solve more equations. So solving equations is what we want to do. And we're going to take all of that machinery and have a good time. But we're not going to forget our polynomials. We're not going to forget our inequalities. We're not going to forget Professor Ron's AC lemma. We're going to take all of that baggage with us, just like we're going to calculus. We're going to take all the baggage from Professor Ron's pre-cal and just plop it on the table and have it to use, because that's what's going to make you strong in calculus, the ability to take this pencil and create mathematics. So I'm so glad that we're back to a standard regime here. Let me click this again to focus. And I'm grateful for the blessing of more calm weather. So welcome back, everybody. And again, I will be doing 2 conference hours today. I have one early and then one in the later afternoon. And so take advantage of that if you need, or you know, get some rest. I mean, last week was so crazy for Professor Ron. I thought, well, I'll be rested, but I wasn't rested because I was stressed. And when the power was off, I froze and stressed about my students and what I needed to do. So again, thank goodness we're back to some form of normalcy. And I hope everybody's getting back to a good place where you feel comfortable. And the fact that you're here, you're still going strong and doing well. So that indeed is a blessing. So if I don't see you at the conference hours, I'll see you at our next class, where we will continue the story about logarithms. So everybody have a great day. Thank you so much. Excellent. So good. Oh, absolutely. Oh, and be safe. Don't waver from that. Kids, I know you've watched the news. 500,000 people have perished from the COVID. It is real. So please take care of yourself. And thank you. You all are so kind. You just the best class possible. So have a great day.